Hello students. So we are already done with one module, numerical methods, that is module 5. Now I am going to start module 2. The name of the module is differential equations of higher order. You guys have already done differential equations in your first semester, right? So the differential equations of higher order we have done in the first semester, first order differential equations. First order, first degree differential equations, right? Here we are talking about higher order. Higher order means the order of the derivative is not just one, but it is more than one. It can be second order, third order, fourth order, and so on. In general, nth order. Okay? So let us see what is that and how are we going, what are such nth order differential equations and how are we going to solve such differential equations, what are the different methods in solving those. All those will be covered in this particular module. Okay, now I don't have to get back or take you back again to what is a differential equation and all. I hope you guys know that. So I'm not going into deep into the more basics because we just did it in your first semester. Anyways, let me just give you a introduction for higher order derivative differential equations. So linear differential equation of higher order with constant coefficients. This is what we are going to consider here. We will consider the general form of a linear differential equation. Linear differential equation. Remember this word. We had linear even in the first semester as well. Linear means first degree. We are not talking about higher degree. Specifically, we confine ourselves to first degree, but the order of the derivative is more. That's it. Okay. So, linear differential equation of higher order with constant coefficients. I'll tell you what is that. What do you mean by that? So, look at this general form. The general form of this LDE. This is an LDE whose degree is 1. So, why do you call it as LDE? Because the degree of every particular derivative here is 1. First thing. Second thing, it is of higher order, nth order derivative. You can see here, d power n y divided by dx raised to n. Okay. So, dy by dx is the first derivative. D square y by dx square is the second derivative. D cube y by dx cube is the third derivative. We know that, right? Similarly, this is dn y by d power n y by dx power n, which is nothing but the nth derivative. And this is n minus 1th, n minus 2th derivative, n minus 3rd derivative, like that. So, we are considering the higher order derivatives. Also, there is a specific term called constant coefficients. What are the coefficients of these derivatives here in this equation? The coefficients here are a1, a2, a3, an, and so on. All these are constants. So they can be variables also, but we confine ourselves to consider an LDE with constant coefficients. Understood? So this is the general form of it, where each and every term represents the higher order derivative, and we always write the highest order first and keep decreasing the order. Okay, in the descending orders of the orders of the derivatives. That is how it is. We cannot consider the degree. It is the orders of the derivatives. Okay. So, nth derivative plus a1 into n minus 1th derivative of y plus a2 into n minus 2th derivative of y plus a3 into n minus 3rd derivative of y, and so on, so on, so on. It keeps decreasing till where we'll get the first derivative with the coefficient an minus 1. Plus, there is no derivative. The function y is as it is. With the coefficient an, and it is equal to phi of x. Phi of x is a function of x in general. Okay. And you can consider the same general equation in the operator form. You remember the operator form where we use the capital D here. So, what does capital D stand for? First derivative d square stands for second d square by dx square. And capital D, similarly, if you can consider the same pattern, capital D power n is equal to nth d raised to n divided by dx raised to n. Okay. So, considering this form here for this particular general form, we get everywhere wherever y is there, we can take it outside here. Rest of the terms will be replaced by capitals. And a1, a2, a3 will be as it is. There is absolutely no change in that. Okay, so d power n plus a1 d raised to n minus 1 plus a2 d raised to n minus 2 plus a3 d raised to n minus 3 and so on till an minus 1 d raised to n plus an into y whole into y is equal to phi of x. So this can be considered as the LDE of higher order derivatives with constant coefficients. Constants means I specifically mentioned here. You guys have to remember that here a1, a2, a3, an and so on, all are exactly the constants. There is not even one single variable involved in that. And also, most of the time, the coefficient of the first derivative, highest order derivative, is supposed to be always 1. Okay, so you can consider this as a function of d. If you consider f of d as this entire thing, so the compact form of representing such a lengthy general form will be this one. And this particular LDE can be of two types. One is homogeneous and the other one is non-homogeneous. Homogeneous and non-homogeneous. Okay, so when do you call it homogeneous? Yes, when phi of x is equals to 0, then we call this as a homogeneous. That means this particular entire equation will take the form f of d into y is equals to 0. So this is said to be a homogeneous linear differential equation with higher order derivatives with constant coefficients. Similarly, when is it non-homogeneous? It is said to be non-homogeneous when phi of x is not equal to 0. So in general, f of d into y is equal to phi of x. That means phi of x can be either a constant or a function of x or whatever it is. It can be anything but except for 0. Such an equation is said to be a non-homogeneous differential equation. Understood? So this is the introduction to the linear differential equation with higher order derivatives. And now let us see how the solution goes. How do we solve that? What are the different methods? Basically, as I told you, we have two types of these. One is homogeneous and the second one is non-homogeneous. For a homogeneous linear differential equation, okay, the solution is said to be a complementary function which is usually represented by yc. Okay, yc is nothing but the solution of this. This is said to be as complementary function. Okay, complementary function. Sometimes people also call it as CF. Okay, next, for a non-homogeneous linear differential equation, the solution will be of two parts. One is yc, the complementary function part, plus we have another part, that is yp. Together is said to be the what is it called? The solution of the non-homogeneous differential equation. We add both of them and we write them equal to y. Okay, so what is yc? Yc is complementary function. When it comes to yp, yp is said to be particular integral. What is that? Particular integral represented by yp. Okay, depending on the nature of our phi of x here, we can find what is that called yp. Now, depending the nature of f of d, you can find the particular the complementary function. So, to find complementary function, f of d is the major part, and to find particular integral, that is yp, that is then phi of x is the major part. Depending on the nature of that, then only we can find the solution. Okay, next, let us see what are the different methods. In this video, we will confine ourselves only to homogeneous, and we'll see what are the different methods to find the complementary function, and hence we will apply it to a couple of problems and see how does it work like. Okay, let me show you how to find the complementary function. Okay, for a given linear differential equation, how do we find a complementary function? See, let us assume the general form of a linear differential equation given by f of d into y is equal to phi of x. Okay, so now consider f of d. F of d is a polynomial in d. Polynomial in d. Okay, instead of x we have d. Okay, so polynomial in d. So how do we solve? We solve a polynomial just like that. In the regular methods, how we solve the polynomial, we solve it in the same way. How do we solve it? If it is a quadratic, splitting the middle term or whatever it is, you can apply the quadratic formula. If it is a cubic, you try factors and then find the other factors. You try first factor and then find the other factors. If it is a biquadratic, try solving it by splitting the factors and then getting at least one of these by trial and error methods, and further by dividing again one more, again further by splitting the middle term, you can get two more, like that. Anyways, you can also use your calculators to check whether the values are correct or wrong, but don't do it directly. Okay, you have to show the solution part. You have to solve the solution part. Directly you can't write it. Anyways, so if the polynomial, whatever it is given for that is the function f of d, how is that? Based on the nature of this, we can write the complementary function. So we can have something called unique roots. You can, what are the values? Whenever you solve a polynomial, you will get a what is that called? Roots of the equation, right? So this is a polynomial equation. We get a roots of the equation. Unique roots. Nature of the roots is unique roots. If you have unique roots, unique means, let us assume we have a polynomial here in cubic. So we will get 3 roots. So let us assume alpha 1, alpha 2 and alpha 3 are the roots. So like that, different values. They are not the same. Unique roots. So whenever you have unique roots, then the complementary function, I will write here, nature of roots and then yc. Like that we can make a table basically. Okay, so in such case, in the first case here, if you have unique roots for this particular f of d polynomial, then the complementary function is supposed to be written as y is equal to c1 e to the power first value, first root alpha 1x plus c2 e to the power alpha 2x. Okay, so let us assume unique roots are alpha 1, alpha 2, alpha 3. Therefore, y is equal to c1 e raised to first value you should take into coefficient of x is the first root. That is c1 e raised to alpha 1x plus c2 e raised to alpha 2x plus c3 e raised to alpha 3x. If you have one more here, alpha 4 roots are there. If it is a biquadratic equation, then we get one more here, c4 e raised to alpha 4x. What if there are the f of d is a quadratic? Then you don't have these two, alpha 1, alpha 2. So c1 e power alpha 1x plus c2 e power alpha 2x. Only these two parts will not come. So depending on the number of unique roots, the number of terms will be written in the yc part. So this will be the solution for f of d is equal to f of d into y equal to 0. This is not there, only equal to 0. So we will consider only the homogeneous equation now, equal to 0. Okay, so we will do the phi of x part later. That is the second part of the solution. Anyways, let us see now second type of solution. That is second type of roots. What could be the second type of roots? What if you have equal roots? Equal roots means sometimes we have You might have done quadratic equation. When you do, you have two equal roots, right? So if it is a cubic equation, you may have two equal roots. Like I have alpha 1, alpha 2. You can see first root is repeated twice. Okay, so when you have something like this equal, I have a cubic equation, and out of which I have first two roots are the same, but the third one is the second root. Okay, different root. So in such case, how are we going to write y is equal to? Whenever we have equal, we have to consider c1 plus c2x. There are two of them equal, so two of terms comes like this into e raised to whatever the equal term is there, that will be the coefficient of x in the exponential form, plus again this one will be written as it is c3 e raised to alpha 2x. What if you have all the three equal? Alpha 1, alpha 1, alpha 1 is equal to alpha. All the three of them are equal to alpha. Then in that case, c1 plus c2x plus c3x square into e raised to whatever this alpha value will be the coefficient of x here, e power alpha x, like that. So when you have equal roots, all of them equal like this, a few are equal and a few are not equal, you can write the combination in this way. Okay, so we also have one more type, that is not real roots, complex roots you call them. So complex roots. So if in case you have complex roots, usually given by alpha plus I beta, plus minus basically we get. Whenever you have complex roots in the form of alpha plus I beta, then the complementary function y is equal to e raised to, there is a real part and the imaginary part in this, right? This is the real part and this is the imaginary part. So alpha is the real part. Real part should go to the coefficient of x in the exponential form, e raised to alpha x into c1 cos, consider the imaginary part, that is beta x, plus c2 sin beta x. Like this you are supposed to consider the complementary function based on the roots. Now you can get a doubt. What if there is a combination of complex roots and unique roots? So how are we going to do that? Such thing can be done in this way. So let us consider there are two roots, alpha 1, alpha 2, and then I have a combination of these where alpha is 0. Sometimes that also happens. So I just have plus minus beta, plus minus I beta. In such case, how are we going to write? So y is equals to, first this one we will apply this method, that is c1 e raised to alpha 1x, plus again we have second one unique, c2 e raised to alpha 2x, plus now coming to this is a complex root, but we don't have the real part, so you can ignore e power 0x, it will become, so it will be next c1 c2, you should take next number, you should not every time take c1 c2 only. So what is the next number here? c3 cos, consider the imaginary part here, beta x, plus c4 sin beta x. This is the way where you can write the combination roots. This is how you get the complementary function. Otherwise, the solution of a homogeneous differential equation, a homogeneous linear differential equation. Understood, guys? Now let me show you quickly with the help of a small example. Okay, so make a note of this. This table is quite very important. With the help of this table only, you can get all the complementary functions. Okay. Now, let us quickly consider one small problem. d cube y, we need to solve d cube y by dx cube minus 2 d square y by dx square plus 4 dy by dx minus 8y is equals to 0. So, the question is like this, and how do we solve? Carefully look, understand the solution. I will explain you step by step. Okay, first step, step 1, you need to represent the given differential equation in its operator form. Operator means using capital D. Okay, so writing this in the operator form, we have d is nothing but dy by dx. So we have a cubic term, so d cube minus 2, this is a second term, second order, so d square plus coefficient 4 is constant as it is, and then dy by dx, so that is d by dx is d. Okay, then okay, so you can just write minus 8. So all of them has a common term, that is y. Y is taken out common from each and every term of this, is equals to 0. You can see this is a homogeneous differential equation. Why? Because the RHS is 0. Phi of x is 0. Understood? Anyways, this is the operator form for the given equation. What is d here? You can write d is equal to d by dx. And so on. You don't have to write. If you can represent for 1, it is understood that d square is d square by dx square, and capital D cube is d cube by dx cube, and so on. Understood? This is the first step. Now step 2, you have something called auxiliary equation. What is that called? Auxiliary equation. What is auxiliary equation? This equation is in the form of f of d into y equal to 0. Okay. So what you should do for the to consider the auxiliary equation, you take up only f of d, and instead of d you substitute m. So you will get f of m is 0. That means here we ignore y and d is replaced by m. Okay. Just to make it easier for us to solve that polynomial. That's it. There is no other purpose of this. Okay. So what does an auxiliary equation show? Auxiliary equation means f of m equal to 0, where this is obtained from the base equation, that is the linear differential equation, f of d into y equal to 0, where in the function f of d is replaced by m. Understood? Now if I replace it by m, I am going to get, instead of d, I should put m. D cube becomes m cube minus 2m square plus 4m minus 8 is equal to 0. There is no more y and all. Okay, don't write y and all. Now this is a polynomial equation in m. How do you solve it? Let us see. We can clearly take out something common, factorize it. So factorizing here, taking m square common, we are left out with m minus 2, and taking 4 common here from these two terms, we again get m minus 2. So take out m minus 2 common, then we get m square plus 4 is equals to 0. Right? So putting each term equal to 0, we get m minus 2 equal to 0, m equal to 2. And then m square plus 4 equal to 0. Guys, there is no minus here, so it won't get split into further factors. So whenever we have a plus, then we have m square equal to minus 4. Here comes our complex roots into the picture. Why? Because there is a negative sign here, and if you have to get rid of the square, we have to give a square root. So we get m is equal to plus minus under root of minus 4. You can write this as plus minus under root of 4i, where minus 1 can be represented as I, and this is equals to plus minus let it be 4 into root minus 1. Okay, that is better. Now root 4 is 2 and under root of minus 1 is I. So our solution for this particular part is m equal to plus minus 2i. M square is minus 4. M will be equal to plus minus 2i. Okay. Therefore, what are all the values taken by m? Therefore, we have m is equal to 2, first value, and plus minus 2i. This is always going to take 2 roots. So, totally, our equation is a cubic equation and we should have 3 roots. Of course, we have 3 roots. One is unique. The other 2 is a combination of imaginary roots. So, what is based on this nature of roots, we can construct our solution called as complementary function. How do you get the complementary function? Therefore, y is equal to, as I just explained you, unique part. That is, this one should go as a coefficient of x in the exponential form. C1 e to the power first value 2x plus, and we don't have the, in this complex function, complex term, we don't have the real part. So you don't have to write the exponential term in that. So instead directly after C1 we have C3 cos, this imaginary part should go as a coefficient of x here. So cos 2x plus C3 sin 2x. Both the terms should come, but the angle for cos and sin is always the same. Understood? So this is called the general solution for the given linear differential equation. Understood? I will just explain within just 2 seconds. One quick glance. Step 1, put the given differential equation in its operator form. Step 2, construct the auxiliary equation. Step 3, solve the auxiliary equation and find the roots of the equation. Step 4, based on the nature of the roots of the auxiliary equation, construct the solution, that is the complementary function for the given linear differential equation, which is here in this case a homogeneous equation. Understood? Yes, we will continue few more problems in my next video.